All right. Good afternoon, everyone. Uh, we've been having some technical difficulties with Blackboard, and so I wanted to take a few moments to go over a few things, chapter 14, correlation and regression. So what I'm going to do today is I'm going to introduce chapter 14. Chapter 14 will be our last chapter that will be covered. And again, this is on correlation and regression. So I'll introduce the concept of correlation. We'll go over how to compute one. And then I'll also talk a little bit about different alternative methods in calculating the correlation coefficient. So we'll talk about what correlation is. We'll talk about different methods and how we do it. And then in class, we'll talk a little bit about regression because we're going to talk about four ways that we use correlation. One of those ways is to predict, and regression equation that we'll be talking about and how we use it. That'll be something that we'll use uh, moving forward. So I really want to just kind of get this up so you all have some reference material as a means to kind of as study materials that you'll need. So I'll go over a few examples. I'll share my screen, the slides, and then we'll also work through a couple of examples. So you'll be able to see how we compute one, and then we'll do a few more examples in class today at 3 p.m. So just giving you a heads up of what's coming forward. I know some of you may not have been able to access the exam, so I'll extend the due date for the exam from to some of you. Again, Blackboard has been down. We've been experiencing some network issues with the university, so very, very sorry for the inconvenience. I've been unable to access materials as well, so we've all been in the same boat. But what I'm going to do, I'm going to show you what chapter 14 is all about. Then we'll talk a little bit more about it in class, and then on Wednesday, should we have class, then we'll go ahead and finish up with chapter 14. All right. So let's do something really quick. Go ahead and go forward. All right. So what we're going to do, I'm going to walk through each of these different outcomes here, these learning outcomes. And so what you'll be able to see is we're going to walk through understanding, um, yeah, understanding kind of what the correlation coefficient is all about. We'll move into how we then compute one. The Pearson R will understand and interpret what the Pearson R is and understand kind of the assumptions and the limitations as a result. Because when you think about correlation and relationship, though we were able to show relationship, we're not always able to then show causation, right? We show that things are related, but we can't say that one thing causes another. And the only way we'd be able to do that is through using um, different experimental techniques that we'll talk about. We talked about with one-way ANOVA, two-way ANOVA, t-test. Those be the only ways that we'll be able to compute and show causation when it comes to showing that one variable causes another. So we'll talk a little bit about that and how that might work. All right. Then we'll talk about different um, alternative ways. Talk about the Spearman correlation. We'll talk about the point by serial correlation, and then we'll also talk about how we compute the phi coefficient. So I'm not going to really talk about how we compute them. Just for the purposes of this class, we're just going to talk about what they are and then what they're used for. And then you'll be responsible for kind of knowing when to use them and why we use them. And then the last couple things is we'll talk about the linear regression equation. We'll talk about how we predict values of the y value based on uh, our x value. So those things we'll be able to talk about and then work through some examples. All right, so these are the things that you'll need to know. There's sum of squares, obviously. We've talked about that for the majority of the semester. Z-scores, which we'll talk about very, very briefly. Hypothesis testing, because again, when we think about um, inferential statistics. We talk about getting a sample of data and then inferring the results from that sample data to a general population. That's kind of what we'll be talking about, even with correlation. And then we'll also talk a little bit about analysis of variance as a mode, because everything that we've been doing is a iteration of the t-test, an iteration of the analysis of variance, and correlation is very, very tied very, very closely to both the analysis of variance that we've been doing and the t-test. And I'll show you how that is as we move forward. All right. So when you think about the correlation coefficient, there are a few things that I want to kind of talk about. And correlation is really just relationship. It shows the relationship between one variable and another variable. So again, two very, very different variables, and we're computing and collecting data on two variables for one individual. And I'll show you what that looks like. So the characteristics of a relationship involve the direction of the relationship. So whether it's a positive relationship where both the x variable and the y variable are going in the same direction, or the negative relationship where one variable goes up and the other variable goes down, and that would be considered a negative relationship. These relationships form what we call a linear model, right? And so this linear model means that as one increases or decreases, there's a relationship that shows that they are related to one another and are in a linear fashion. And so what we want to see is we want to see a strong relationship. We want to see an increase or a decrease in one variable or the other, right? And so the strength or the consistency or that coefficient that we'll talk about, it ranges from a value of 0 to a value of 1, where 1 is very, very consistent, very, very strong, and 0 is no correlation, no strength, no consistency whatsoever. So we talk about patterns a lot when we talk about correlation. And correlation is all about how one variable is related to another, right? We want to see that relationship. And there is a degree of linear relationship, or how well our data points that we have for, again, we have two data points per individual, how they um, fit a straight line or a predicted straight line, which we'll talk about. Because there is a line or an imaginary line that goes through the data, and we want to see how much that consistency, how strong that pattern is, how clustered together are those data points around that imaginary line that we'll talk about. And then we also think about characteristics that are all independent of one another. So one variable is not dependent on the other. And when you think about each data point, they're all independent. They're not dependent upon a single variable or a single person. So here's an example of a some data, what we call a scatter plot. So on the right-hand side, what you see is you see the scatter plot here, right? And so these dots are corresponding to these data points here. So for person A through N, we have family income, which is, we'll call that our X variable, and we have student average grade, which is their Y variable. So if we were to label this, this would be, let me do this real quick for you. This would be our X variable, and this would be our Y variable. And so what you see here, this is our Y axis right here, and this is our X axis. All right. So for each variable, you see an individual data point for each. So for A, right, for student or person A, their family income is $31,000, right? So $31,000 is around this area right here. And their grade or average grade is 72. So this singular point is where those two variables meet, right? Let's go to person N. So their family income is $174,000, and that is all the way out here. And their average student grade is 95. So this $174,000 here, and we see that they have an average grade of 95. And you see everything in between, right? So everything you see here is their family income and their student average grade. And so that's how those points are plotted, right? And this is what we call a scatter plot here. And this is just our data with our X variables and our Y variables listed here. But again, for each individual person, they have both an X variable data and a Y variable data point for the Y variable, right? So here are other examples. When you think about the relationship and you think about the pattern in which they go, as you see, the performance in class, which is your Y variable, and time spent studying is your X variable. All right. So it shows that in this one right here, that as you spend more time studying, going from 0 to infinity, your performance in class, maybe that's your grade, goes up. So the person who spends the most time studying usually has the highest grade. And again, it's not that it's always the case, but the pattern you see here is that as you spend more time studying, your performance in each class will increase. The opposite is true when you look at the X variable for smartphone use. So as individuals use their smartphone more and more, right? So as you use it more going on this X axis here, you see lower grades. When they use their smartphone less, the performance in class is a little bit higher. But again, you see that even if you use it more, doesn't always mean that you're going to have low grades, because you see this person right here, they use their smartphone pretty often, but their grade is moderately high, right? So again, this is just a pattern that when you think about relationships, when you think about correlation, we're showing patterns of behavior in two variables and the relationship between those two variables, right? So we talked about how we talk about the different values, the coefficient, and it varies from 0 to plus or minus 1, right? So this variable, we have your y-axis on this y-axis here and your x variable here. This shows a perfect negative relationship, meaning that for every change in y, you see a corresponding change in x. And so this is a perfect relationship. And you see this line here, right? That line is that imaginary line that our data points are lining up, lining on, right? And so that's a perfect negative relationship. These coefficients cannot be any greater than 1 and can't be any less than -1, right? So they're somewhere between -1 and +1 and somewhere in between. So what you see here is for this example with a correlation of 0, there is no real pattern whatsoever, right? There's no, there's no uniformity here. There's no consistency. The strength is very, very weak. You see how they're very, very dispersed, and this kind of randomly dispersed. In this example, you see a 0.90, meaning that they're clustered really, really close together, and there is a consistency in the pattern of these data points, right? So they're going up and to the right, which is positive, down and to the right is negative. And so this is you see the consistency is somewhat there for this example here, but again, it's not as strong as this. And so when we think about the magnitude of the strength of a correlation, we're only worried about the point value here. So zero point 0.9 and zero point 0.4, right? So zero point 0.4 shows the consistency or the strength, and the positive or the negative just shows the direction in which the relationship goes. Either a positive relationship where you see as the y variable increases, then the x variable also increases. But in this instance, you see that as the x variable increases, the y variable decreases. And that's what the negative and the positive relationship show. All right. So when we're measuring the degree and the direction of our linear relationship between these two variables, there is a way that we compute these changes, right? So again, for a perfect linear relationship, we saw in the previous example in that -1, when we go back here, when we look at that -1 relationship there, every change in x has a corresponding change in y. And that could be either a negative, perfect negative relationship, or a perfect positive linear relationship, where again, every change in x has a corresponding change in y. When there is not a perfect linear relationship, that is not always the case, all right? Because again, where there is a lot of difference in individuals, the scores, the data points are going to be different based on the person that we have. And so you're going to get usually something like this or like this, or even like this. You're likely never going to see, well, not never, but you will likely very, very rare to see instances in the real world where you'll see a perfect negative or perfect positive relationship. But you will see something like this where you see a positive, pretty close to a perfect positive relationship between your x and your y variable. Right? Here is what we will be doing. This is what we'll be computing, right? So we have our correlation coefficient, which is represented by the value of R, okay, this little lowercase r, and we're looking for the covariability in the numerator of x and y together, right? So how do x and y covary? How are they correlated to one another? How do they move in relation to one another? And in the denominator, we have the variability of the x and y separately, meaning we're taking the two variables separately and we're looking at the variability between those two at a separate way. And we're combining those two variabilities together. And then the numerator is the variability of x and y together. How do they covary with one another? All right. So there are going to be two things that we'll need in order to calculate our R. Okay. The first thing that we're going to need is the sum of our products of our deviations. And I'm going to show you how we calculate that with an example. All right. But the sum of products is essentially this formula right here. So what we're going to be taking, and this will look very, very similar to you, is this particular equation. These are our deviations for our x value and our deviations for our y value. And we're again taking the sum, excuse me, the product of the deviations together, and then we're summing them all together. And I'm going to show you two ways in which we do it. This is the definitional formula, right? Where you're summing the deviations together. You're getting the products of those two deviations, the y and the x value, and then you sum them all together. And then this second computational formula, which is a little more simplistic, where you don't have to really worry about all these the decimals and all those things. You can use the computational formula, which is a lot easier, and I'll show you both ways so you'll get an understanding of how we use them. But again, very, very, very easy. This will be go in your this will be this top part, right? So when you think about the covariability of x and y, your sum of your products will be the numerator, and then your sum of squares for your x value and your sum of squares for your y value will be in the denominator, and I'll show you what that looks like. All right. So here again, here's the computational formula, and again, just pause and record these formulas because these are things you'll need. But again, we're going to use these in order to calculate our correlation coefficient. Okay. So here's an example. All right. So our X values are listed here. You got 1, 2, 4, 3, and our Y values are 3, 6, 4, 7. All right. In order to get our deviations, the first things you have to do is calculate your mean for your X values, which is 2.5. So you'll add these together. You got 1, 3, 10 divided by 4 will give you 2.5. And you have 3, what's that, 10, 20. 20 divided by 4 gives you 5, right? So this is the mean of X, and this is the mean of Y. In order to get your deviations, all you do is you subtract your mean value from your X value here. And so you get 1.5 here, negative half, positive 1.5, and positive half. And again, you get the deviations, you do the same thing for your Y values, right? So you have your Y value is 3 here. You have 3 minus 5 is -2. 6 minus 5 is 1. 4 minus 5 is -1. 7 minus 5 is +2. All right, so now let's see what we do. All right, so again, to get our SP, you take your deviation here, you multiply it by the deviation for Y, and you get a +3. -1/2 times -2 gives you a +3. 1 times -0.5 gives you -0.5. -1 times -0.5 gives you a -1.5. And then 2 times 0.5 gives you 1. And then once you get all these values, you sum them together and you get a value of 2. So this is how you calculate it using the definitional formula. So now let me show you how to compute it using your using the computational formula. Let me share my screen so you can see what I'm doing. All right. So if you go back to our example, right? So we have X, and our Y. We have 1, 2, 4, 3. We have 3, 6, 4, 7. And this is our computational formula here, SP sum of x, y minus the sum of x, the sum of y, all over n. Okay. And n in this example are the number of pairs that we have. And so in the example that we have one, two, three, four pairs. So our n in this particular case is going to be 4. Right. So now let's do some math and computation. So our x value here is 10, and our sum of our y value is 20. Okay. All right. One other thing that we need is our x, y. And so we have to multiply 1 times 3 is 3, 2 times 6 is 12, 4 times 4 is 16, 3 times 7 is 21. And to get our sum of our x, y, that should be 52. All right. So it looks like we have everything that we need. We have our sum of our x, y value. We have our sum of our x, our sum of our y, and we have our n value. So let's compute our SP. And you can see that it's a little bit easier to do instead of having to do all the deviations, compute the mean, all that stuff. Now we're able to do that. So now we have 52 minus 10 times 20 divided by 4. So what you should get is 52 minus 200 divided by 4. So that should be 52 minus 50. So SP should equal plus 2. All right. So again, very, very simple. Again, you could do it the definitional way, or you can do it the computational way. The computational way is a little bit more simplistic, and it doesn't take as much time. And so I will use this one more often than anything, just so I don't have to go through, get all the deviations, get the mean. It just makes it a little more simplistic for me. All right. So let me stop sharing this, and let's go back to our slides. Let's go back here. Share. All right. So again, you see the same value here, plus 2, and our and when you think about your computational way, so again, you have, go back. So we have our definitional way, which we got here, and then we did our computational way, which is very, very simplistic. Got our x, y, got some of our x, some of our y, and our n value, and we got the same value. You should get the same value no matter what definition or which formula that you use. All right. So in order to compute our Pearson correlation, the coefficient for our R, we need two other things in order to calculate it, right? So the SP measures the covariability of our X and Y variable here, right? This is the SP. And in order to determine our variability of X and Y separately, in the denominator, we need the square root of our sum of squares for X and our sum of squares for Y. And so again, we know how to do sums of squares. Again, you get your deviations, you then square them, and then you work through getting the rest of that, right? So what I'm going to show you is how we're going to do that, and how we do that. Very, very simple, very, very simplistic. And what you'll see is we're going to go ahead and calculate the Pearson R. And as we calculate it, you're going to be like, man, this is really, really simple. But again, you want to be able to calculate your R to show the correlation between variables in order to show the strength and the consistency and even the pattern in which the correlation is going. All right. So again, write down, this is the formula that you'll need. You want to write down this correlation formula. Again, little r, which is correlation coefficient. We know how to get our SP. And again, I don't have to show you how to get the SSX, but I'm going to go through an entire example for you so you're able to see how that's done. So we're going to do sum of squares for X times the sum of squares for Y, and everything's going to work out the way it should. All right. So let's go ahead and work through an example. Okay. So this is the data that we're going to use. You have your X variable here and you have your Y variable. Okay. So you want to write these variables down. I'm going to go to my next example so that you're able to see what that looks like. Okay. What that looks like. So let me go to my data and then you'll be able to see kind of what and how everything functions. All right. So let's go ahead. After you write this down, then we're going to go ahead and do some work. All right. But again, these are my X and my Y variables that we're going to be using in order to calculate our correlation. All right. Let me share my screen again, my whiteboard. All right. So as you can recall, right? So we have our X value, which was 0, 10, 4, 8, 8. And we have our Y variable, which is 2, 6, 2, 4, 6. And so what I have to do, if you can recall, let's go with our R equals SP, the square root of SSX, SSY. Okay. So we have to get all of this information. We know how to get our SP. All right. We're going to do that, but we got to get everything else that we need. All right. So for our sum of our X value, we have 30. For the sum of our Y, we have 20. All right. And so I have 1, 2, 3, 4, 5. So in order to get my mean for my X, that's going to be 6. And a mean for my Y is just going to be 20 divided by 5, excuse me, 4. If you can recall, we need a few other things to do. So what I'm going to do, I'm going to go ahead and get my X, Y. So to get that, we just multiply again, 0 times 2, 0, 10 times 6, 60, 4 times 2, 8, 8 times 4, 32, 8 times 6, 48. So to get my sum of my X and Y, that should be a value of 148. Right? All right. So now we also have to get our N, and our N for this equation is going to be 1. We got 1, 2, 3, 4, 5 pairs of data. So that will be 5. Okay. So we know how to get my SP. One other thing that I'm going to need to know and how to compute is my deviation. So we're going to got to get our deviation squared in order to calculate our sums of squares. All right. So in order to get our sums of squares, we're going to have to, I'm going to go ahead and delete this. Now I'll move this down below so you can see it. R equals SP sum SSX times SSY. That's there. All right. So now let's go ahead and get our deviations. All right. So deviation for X. So we have 0 minus 6, which is negative 6. Oh man, where am I? So deviation. So again, we got 6 here. So 0 minus 6 is negative 6. 10 minus 6 is 4. Okay. Negative 2, 2, and then 2. All right. For my deviations for y, you should get negative 2. So 2 minus 4 is negative 2. What is that? 6 minus 4, that's 2. You should get negative negative 2. You should get 4 minus 4 is 0. And then you should get 6 minus 4 is 2. All right. So let's keep going. So now deviation squared. So deviations for x squared and deviations y squared. And all I'm doing is squaring these values, right? So negative 6 squared is 36, 16, 4, 4, and 4. So negative 2 squared, 2 squared, 2 squared. All right. Next, we have negative 2 squared, 4, 4, 4. 0 squared is 0. And then 2 squared is 4. All right. So now our sums of squares for x equals 36 plus 16 plus 4 plus 4 plus 4. That'll give you a value of 64. And my sums of squares for y, 4 plus 4 plus 4 plus 4, that's 16. All right. So now we have everything that we need. All right. Everything that we need is listed here. All right. So in order to get my SP first, I need to calculate everything here. So that's going to be 148. So we'll write it out so you can see it. Minus x y over n. So we have SP equals 148 minus sum of x is 30 times 20 sum of y divided by 5. All right. So everything should flow really well now. So we got 600 divided by 5, 148, 148 minus 120. So SP should equal 28. All right. So now got everything I need now. All right. So for my R, got 28 in my numerator. Okay. That's the covariability of X and Y. Okay. Then I have, again, the variability of my X and my Y variable separately listed down here. So that's going to be the square root of 64 times 16. Okay. So that'll be 28 divided by 32 equals 0 point, that'll be plus 0.875. All right. So again, we have a correlation of 0.875, which is a really, really strong correlation. You see that there is some correlation there. You see that there is uh, a strong relationship between our X variable and our Y variable. And if I were to plot that, which I'll show you, and again, make sure you record this, pause and go through each of the steps, okay, so that you can see kind of how everything is written out. But again, everything works out really, really well. You see that you have let me get my pointer so you can kind of see. I'll walk you through it a little bit. Dun, dun. See, pointer. I think you can follow my cursor. Yep. So what you see here, we have that, we have our SSY, we have these things, which is really, really important, right? You got to have your N value right here in order to to uh, get everything you need for your R. All right. So again, those are some of the key things that you'll need. Have to get your sums of squares for your X value. have to get your sum of squares for your Y value. Those are how we measure our variance for X and Y separately. And then the covariability for X and Y is measured by SP, which we talked about up top in the numerator. So again, now we're showing the relationship between X and Y and how we may be able to predict X from Y and Y from X just based on what we've been given. All right, so let me stop sharing and then we'll go a little bit further. Right. Yeah. Okay, so I'm going to show you again everything that we just did. It's located here. Let's go ahead. So this is the scatter plot for the data that we've collected. Again, you have 0, 2, 4, 2, 8, 4, 8, 6, 9, 6, excuse me, 10, 6, right? So you're able to see that these are the five data points, and all of those correlate to these values here. Okay. All right. And so this is what we did. Okay. This is what we did. So you have your, this is the definitional formula here, right? The way they did their sums of squares and the way they got their sums of the product here. All right. But we did it the computational way. But again, you can also do it using the definitional way as well. Okay, very, very easy to do. But again, everything that you see here is how we calculated it. So again, walk through these a couple of times. I'll give you a couple of examples in class, so you're able to kind of get a grasp of what we've been doing. All right. So when you think about correlation, okay, what we've been doing, correlation is also related and can be expressed as a relationship among z-scores. Why? Because for every x value, every y value, there is a corresponding z-score for each of those scores, right? We talked about knowing your location of your score and how it relates to the mean and to other people in the distribution, right? So if you're looking for and calculating your z-score, then you can also use your z-scores um, uh, to then calculate or compute a correlation coefficient, right? We're not going to do that, but again, this is how you would do it for a sample. Okay, and notice that we're using n minus one for a sample, and we're using big N for the population. And so this is rho. This is a rho, the Greek symbol for rho. And again, this is for the population. This is for the sample. Okay. But again, z-scores, again, like we talked about before, they help us to identify our exact location for each individual score. And so this is how you would calculate it. We're not going to do it. We could, because we know how to calculate z-scores, and I might show you how to do it in your in class, but we won't do it via the recorded lecture. All right. So here is a question. We talked about consistency. We talked about the fit, right, around that imaginary line, right? The closer uh, the, the dots or the data points are to one another, that means you have a strong, very, very consistent relationship between your X and your Y variable, right? So here's a learning check. It asks, it says, a scatter plot shows a set of data points that fit very loosely around a line that slopes down and to the right. And remember, when a pattern of dots, data points slopes up and to the right is positive, down and to the right is negative. Okay, so let me show you really quickly so you can see. So up and to the right is positive, down, up, down and to the right. Let me erase that. Down and to the right is negative. So let me get this correct. So down and to the right is considered negative. All right. So you got up and to the right positive, down and to the right negative. All right. So it says down and to the right. So we know that it's not going to be A or B because it's down and to the right here. We know it's got to be somewhere in C or D. All right. So it says which of the following values would be closest to the correlation for these data. And since we know that the data points fit very loosely around the line that slopes down and to the right, then we know that it's probably going to be around 0.35. Because again, not knowing what the data looks like, if it's something that's loose, it's going to be closer and closer to zero. So anything closer to one is tightly fitting around the line. Anything closer to zero is loosely fitting around that line. All right. True or false? It says a set of n equals 10 pairs of x and y scores has a x and sum of y, and a sum of xy equals 20, equaling 20. It says for this set of scores, the SP equals -20. So that will require you to solve, right? So we know that you have the sum of squares, excuse me, the sum of x and y minus the sum of x times the sum of y divided by 10, right? So what you should see is, and let me see if it'll help, let me do it. I mean, it might not. It usually messes up. So it'll be 20 minus 20 times 20 divided by 10. So all you got to do, solve it out. 20 times 20 is 400. Okay. 400 divided by 10 is 40. 20. So yeah, this will be 40 here. Sucks that it always does that. So this will be 40. This will be 20. Up, 20 minus. So that should be minus 20. All right. So that is true. All right. So it says for the second one, if the y variable decreases, when the x variable decreases, there is the correlation is negative, right? So it says as one variable decreases, then the other variable also decreases. If you can recall, right, if they're going in the same direction, that means there is a positive relationship, okay? If they're going in the opposite direction, that means there's a negative relationship. So this one should be false. All right, so the first one is true. Second one is false. All right, let's move right along. All right, so when you think about correlation, okay, correlation, they have a number of different applications when it comes to using it in the real world. Okay, so for us as researchers, as social scientists, we use correlation in a number of ways. One of the major ways that we use correlation is to predict. Now, again, uh, correlation does not show causation of any by any means necessary, right? But it does give us an opportunity to see patterns. So we know that if you study more time, you take more time during the week to study, we know that on average, the pattern is that if you study more, your grades will be better, right? We know that. That's a pattern that you see from student to student, right? Now, there will be some individuals who study more and don't score as highly, but we know that on average, if you study more in a class, you're going to have a higher grade, right? So we use one variable to make predictions about the other, right? So I know if I look at, everybody's studying habits, if you're studying more, then I can almost predict how high your grade will be. And again, that's not for everyone, but that's the pattern that you see. All right. So here's an example. Again, ACT scores predict college GPA. So this the higher your ACT scores, usually the GPA of college GPA is a little higher. Right? Validity. When you think about validity, validity is measuring what you intend to measure. So for instance, if I am measuring, if I have a scale and I want to measure, let's say, self-esteem or self-efficacy or confidence, right? I will then use my correlation for each of my individual items that I have in my questionnaire. Say I have 10 items. I'm going to correlate those items together to see if those items are either, excuse me, we'll talk about reliability and if they are valid, right? So if I have one item asking if I feel good about myself, and I have another item that says I don't really care about what people think, and they score the same, right, then I have a really, really high validity and I'm measuring what I intend to measure, right? So here's an example. It says a new test of IQ compared to other proven methods of testing IQ, right? So if the higher IQ scores are that you get from the proven methods, and then you have a new test of IQ, and they all are correlated to one another, then you know that you have a valid measure, meaning my test of IQ is correlated, highly correlated with the other tests and how other people score on those other tests. So here's an example, perceived stress scale, right? If I want to see if your stress is is high compared to other ways in which we measure stress, say I measure stress based on your cortisol levels, right? So if your cortisol levels are high, then your stress levels should also be high, right? So again, if your cortisol level is high and your perceived stress scale score on this particular scale is also high, then I know specifically that I have in measuring perceived stress. So again, cortisol levels are really, really high and perceived stress scale score is really, really high. Then I know I'm measuring the same things. All right. The other things is reliability. All right. So reliability is all about, is your measure really, really stable? Do you get consistent measurements every time? So for instance, if you were to step on a scale, a weight scale, and you weighed yourself every morning for 7 days, what you would expect is that you're going to be around the same weight each time you step on the scale. Now, again, depends on how much water you drink, depends on how much food you eat, but it should be really consistent, be really stable, right? So that shows reliability in a particular measurement. However, say you got on the scale every morning for 7 days. On the first day, you got a score, you got a weight of 185. The second day, you got a weight of 163. The second day or the third day, you got a score or a scale measurement of 203, right? Those are so varied, meaning that it's not a stable and consistent measurement of weight because maybe your instrument or your measurement tool is not calibrated right, right? So you want that measurement to be very, very consistent. So again, taking the same test twice, you should see very, very similar results. Just like stepping on a scale at the same time uh, for each particular day in the morning, you should see a similar weight, right? No matter what you eat, drink, unless you binge out on food. But again, if you're again eating the same, you should see the same scores. Last thing is theory verification, right? So in order to test a theory, I have to determine if there are correlation between two separate variables, right? For instance, um, there has been research that shows that the intelligence of the parent is highly correlated with the intelligence of the child, right? So does a parent's IQ predict their child's IQ? Now, we can't predict it one to one because again, with environment things and schools and everything that happens, all the environmental things that happen outside of, the parent and the genetics we talk about, then, there may be some differences, but there has been research to show that a parent's IQ does in fact predict the child's IQ. And there is there are other factors that contribute to IQ, like again, what school you go to, what type of stimulating environment you're in at home, how many books you read, language, but all those things matter as far as predicting someone's IQ. But again, at base level, when you think about genetics, your parent's IQ is a good indication of what your IQ will be. If your parent has a high IQ, that means they're usually going to be a little more conscientious. They're going to have higher work ethic or bigger work ethic, and so that's going to provide a model for the child. And so that's when you start to see the prediction and the kind of verifying that theory. And again, a theory is verified by providing additional evidence to support it, right? So if we see that for, let's say, 200 parents, we take their IQs and then we use the correlation of parents' IQ with the child's IQ, right? And you see a high correlation, say 0.7 or above, right? Then it's safe to say that you can kind of verify that theory that parents' IQ does in fact predict children's IQ, right? All right. So one other thing that we'll talk about and I have a few more slides I want to go over. Then I'll cut this one off, this lecture off. Correlation, again, does describe relationship, right? So again, as we showed different ways in which we can use it. We do and are able to show relationship. So again, if you're looking at a parent's IQ versus a child IQ, there is a relationship between the two, right? But we cannot and do not demonstrate causation, right? So we can't say that the parent's IQ causes the child's IQ to be at a certain level. We don't know. We can't do that. Or, for instance, we can't say, for another example, we can't say the number of hours that you study each week gives you or causes you to get a particular grade on an exam. Now, there are other factors that can contribute to you getting a particular grade on an exam, right? So, yeah, studying is a factor, but it's not the only factor. So it can't show strictly just causation. In order to show causation, has to require some type of experiment, right? Where you're manipulating one variable and then you're controlling other variables that could impact it. Those we call them extraneous variables that have an influence on what we do. All right. So on the next slide, you'll see how in example 4.14.4, it demonstrates the fallacy of attributing causation after observing a correlation. And it's again, just because two things are correlated does not mean that they are and cause one another. For instance, um, the level of ice cream consumption and the incidences of shark attacks increases are that they are it's a positive correlation, and it's actually really highly correlated, probably zero point 0.9 or higher, right? So you got shark attacks and ice cream consumption, they have a positive correlation. Now, those two variables are correlated, but there's some underlying factor that causes them, and that would be temperature, right? So as the temperature increases, more and more people eat ice cream. And as the temperature increases, more and more people are at the beach, right? And so that just increases the likelihood that there might be some type of incidence with a shark attack, right? But again, it does not show causation whatsoever. So here, again, here's a hypothetical data showing relationship between the number of churches on your x-axis and your number of serious crimes, right? So it shows number of churches increases from 0 to say 70 churches, and your number of crimes also increases. What could be the underlying factor here, right? When you think about the number of churches, you think about the number of serious crimes, think about that. And when you think about the underlying variable here, it might just be population, right? With population increase, you're going to have more and more churches being created and established, right? And as more and more churches are established, again, you need more and more churches. And when you increase the population of a particular area, then you also increase the incidence or likelihood that there are going to be more serious crime, right? You have a more condensed area. I mean, you're going to see more and more people, having crimes, right? So it doesn't mean that the number of churches causes the number of serious crimes, right? There's an underlying factor that contributes to that. Some other things to consider. Other things to consider: correlation coefficient. Again, the value, the size can be affected by the range and the scores, right? How do you, again, going back here, right? You see the range goes from 0 to 70 and 0 to 60. It's a really, really good range, right? But however, think about this. What if I I just cut off the number of churches at 40, right? So say I just drew a line here. Yeah, let's draw a line here at 40. That's not a straight line. And I just cut off all these churches right here, right? So now it was a linear relationship as you see it going up and to the right here, right? And I'm making a mess. Let me go back, delete some of this stuff. So you see that positive line going up and to the right there. And then you see that I've eliminated this data right here, right? So by eliminating this data, I'm changing the correlation a little bit, right? I could be strengthening the relationship here, or I could be making it a little less, right? And so we have to think about restricting the range. If I just limited it to 40 churches, then I don't and I don't incorporate these data points, which affects how I use and how I interpret the correlation itself and what the correlation will be. Right? So go back to my pointer. Okay. So again, when you think about this data, right, this data right here shows a lot right here, right? It shows a really, really close and consistent and clustered together these lines, right? This is a good correlation, really, really high correlation, right? But if I just looked at this restricted range and did not think about the information to the left over here to the left, right? Then I go from a positive correlation to something that's not really correlated whatsoever, right? So say for instance, I have this is my population right here. All of this is my population, okay? And then I just take this little sample out here, right? I restrict it, right, to this limited range over here. And now my population, my sample right here, it becomes very, 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 very small. I mean, there's no pattern whatsoever. So the correlation will be very, very low in this particular instance, right? Just showing you a few things that can go wrong when you restrict the range of a correlation. One other thing that will affect the correlation coefficient is outliers, right? And an outlier is an individual with an X and or Y value that is substantially different from other data in the sample. For instance, in our class, mostly everyone is around 5'6", 5'7", maybe 5'10", right? And then we have somebody in our class that's 6'3", 6'4", right? They would be considered an outlier, right? Their height is substantially different from other data in the sample. For instance, say we had someone who was 7'1" in the class, right? They would be considered an outlier in height because now they are substantially different from other data, and you'd see that their data point would be considerably outside of the range. And I'll show you what that looks like. In a scatter plot, the point is clearly different, and you can see it. It's different from all the other points. You see all the other points kind of clustered together in one way, and then you see the scatter plot where that one outlier is out there to the by itself. It's kind of hanging out there by itself. And outliers produce a disproportionately larger impact on the correlation coefficient. And I'll show you what I mean by that. All right. So for instance, here is an instance where we have, this is our original data here, right? A through E, right? This is the original data. The correlation coefficient here is a negative 0.81, excuse me, 8, negative 0.08, right? And so you see that it is kind of slightly, slanted down into the right, okay? However, if I were to incorporate this extra data point here with the outlier included, 1412, you see that that push that point way out here. And that would then also take this, what was at one point really no correlation whatsoever. It then disproportionately affects the correlation coefficient and increases it to a positive 0.85, which is very misleading. So as researchers, what we usually do is we would then remove these outliers because again, there might be something that just is extremely different about this person, and you'd probably want to remove them in order to make sure that you get an accurate correlation coefficient for the data that's presented here, right? So if you do have outliers, oftentimes there are instances where you would remove the outlier in order to get something that's a little more accurate with your data. Right? Last thing that we'll talk about is our effect size measure. All right. So when you're getting your effect size, and we'll talk about hypothesis testing, we'll go over that in class. But when you're thinking about your correlation coefficient and it is measuring the degree of a relationship between two variables on a scale from 0 to 1, right? We know that anything close to 0 is kind of little to no relationship whatsoever. And anything close to 1 is a really, really very, very high correlation, right? So it is easy to mistaken this as a proportion, but it's not, right? It's not. It is really just a degree of relationship between two variables. However, in order to calculate your effect size measure, we call that our R square, right? All you do is you take your R, or your correlation, and you square it, right? A squared correlation would then become what we saw in our t-test, the r square value, right? That is the shared proportion of variability, right, between our x variable and our y variable, right? So when you talk about your squared correlation, this is called the coefficient of determination, and this is considered our effect size measure. So let me write this out. So this is our effect size. I'm sorry, it might skew a little bit, okay? But this is our effect size measure, right? The coefficient of determination is our effect size. So when we take our R or our correlation and we square it, that then becomes our effect size, all right? And so we talk about the amount of variability that is explained by one variable and the other, right? So if, for instance, if we had a value of, let's say, zero point 0.8, right? A value of 0.8, what about the laser? A value of zero point 0.8 is your correlation. For instance, let's say studying, the amount of time you study and the grade that you get in your class, let's say the correlation is zero point 0.8, all right? So this means that if I square this correlation, then 64% of the variability in the y scores can be predicted from the relationship with x. So for instance, this says that 64% of the variability in my grade is determined by the amount of time that I study in class, right? Or the amount of time I study outside of class, right? Meaning 64%, right? That's a really, really good percentage. However, there's another 46% of the variability in my Y scores that is explained by something else, right? Maybe it's your prior knowledge of the data or the other information. Maybe you're getting tutoring outside of class. Maybe your mom was a statistics major or a statistics professor, and they helped you when you were very, very young, right? All of those things might explain the rest of the variability, but we know that 64% of the variability is explained in your grades based on how much time you spend studying. All right. So again, you want to kind of go through this. This is our effect size measure, the coefficient of determination. That's our R square. Just like when you solve the t-test, that's how you get your R square measure. All right. So again, here are just degrees of relationship, right? 3 different degrees of linear relationship. You have your IQ scores and you got your shoe size. This has pretty much no relationship whatsoever. Can't really predict anything. You can't predict your IQ score for using your shoe size. You can, however, predict, your high school GPA based on your IQ score, right? So IQ scores, are, pretty predictive. Doesn't give you everything, but it does give you a little more information. So you might be able to predict your college GPA based on your IQ scores. But again, there's information where you have to think about, if this is, say, for instance, say 0.6, right? So let's say, for instance, this is 0.6, right? So this is my R. That means my R squared is 0.36, okay? And so 0.36 is my variability. And if my 0.36 is my variability, that means 36% of my variance in GPA can be explained by IQ, right? So that's a little bit, I mean, that's pretty good at percentage, but that means that there are other things that can explain college GPA, like your high school GPA or your work ethic or your self-esteem or whatever that is. 36% is explained by IQ scores, but we know that there are other things that can explain it. All right. Your annual salary. This is a positive. uh, for our annual salary, we know that this is a one-to-one relationship. So you got your monthly salary and your annual salary. So as your annual salary increases, your monthly salary increases by the same amount, right? Again, this is a one-to-one relationship, meaning if your annual salary increases 100%, the variability in your monthly salary is explained by your annual salary 100% of the time. That means you can predict your monthly salary from your annual salary every time, right? That's a one-to-one relationship. That means your correlation coefficient is one, and your R squared is also one, right? Okay, so I'm gonna go ahead and stop here, and then we will pick up on 14-4 in class. All right. If you have any questions, again, rewind, go back, and then again, if you have any questions in class, let me know. We'll go over. I'll kind of review a lot of this stuff in class, and then we'll talk about the hypothesis test and some other things that we need to talk about with correlation coefficient. All right. So let me stop sharing, and I will see you all very soon.